Assalamualaikum warahmatullahi wabarakatuh. Kami dari kelompok 1 akan mempresentasikan mengenai control unit operation dan microprogrammed control. Nah, bisa dilihat di sini ada sebuah library, dan di sebuah library ini memiliki beberapa fungsi. Yang ini import OS. Import OS ini sebuah fungsi yang akan berinteraksi dengan sistem operasi yang ada, misalnya Windows atau Linux. Sedangkan import time ini fungsi yang ada hubungannya dengan waktu. Dan yang OS ini bawaan dari Python, dan time ini buatan sendiri. Lalu ini ada menu splash screen. Di sini ada inputan user yang kami beri nama user ini sebagai variabel tampungnya. Dan di sini ada os.system cls. Nah, di sini untuk nge-clear screen. Lalu ini ada output. Jadi tadi setelah di-input kan namanya siapa gitu lah, maka di sini akan ditampilkan di output dengan memanggil user tadi itu. Lalu ini ada time sleep. Nah, ini untuk delay. Delay ini untuk jeda waktu tunda. Nah, di sini ada 3, berarti 3 detik. Dan ini di clear ya, clear screen. Lanjut. Di sini ada tulisan program akan segera dijalankan. Terus tunggu 3 hitungan. Nah, di sini ada clear screen. Lalu time sleep-nya ini 3 detik, berarti nanti dia jedanya 3 detik, 3 detik, 3 detik gitu. Jadi 1, 2, 3. Nah, kalau sudah ada 3 hitungan gitu, lalu akan muncul output program berhasil dijalankan. Silahkan isi di bawah ini. Nah, dalam sistem ini terdapat array, ya, array 1 dimensi, yang mana ini binary, dan yang di bawahnya glibs. Dan binary ini mencakup beberapa numerik biner, dan glibs ini sebuah karakter. Jadi ini masuk ASCII lah kurang lebihnya. Lalu di sini akan ada inputan user yang kami beri variabel tampung, yaitu keyboard. Lanjut, di sini ada equal, atau bisa dibilang komparasi, membandingkan. Jadi di sini ada perkondisian. Jika keyboard sama dengan glibs 0, maka dibuatlah variabel tampung yang bernama temp, dan itu menampung binary array array ke 0. Nah, ini array ke 0. Jadi nanti akan menampung array ke 0 ini. Nah, terus ini selanjutnya juga sama seperti itu hingga 94, array ke 94. Jadi dia akan melakukan hal yang sama hingga array ke 94. Selain itu, maka program akan mencetak error. Nah, di sini di dalam sistem ada swap atau pertukaran data, ya, nilai-nilai data nanti akan ditukar. Jadi di sini ada keyboard, ya, keyboard, nilai-nilai dari keyboard akan masuk ke variabel tampung bus. Lalu variabel tampung bus tadi nilainya akan dimasukkan ke variabel alu. Lalu nilai dari variabel alu akan masuk ke variabel tampung main memory. Lanjut. Nah, ini ada output. Data telah diproses oleh alu dan disimpan ke main memory. print data sama dengan, nah di sini untuk output ya memanggil nilai dari main memory, dan yang di bawahnya ada kode biner. Lah ini memanggil binary tadi yang berada di variabel tampung temp. Dan yang terakhir, program munculkan output program berjalan dengan baik sesuai prosedur. Oke, langsung kita testing aja. Nah, kita klik run. Nah, ini ada masukkan nama Anda. Misal kita beri nama Heri Karyono. Nah, maka akan muncul selamat datang Heri Karyono di aplikasi Control Unit Operation dan Programming Control. Nah, di sini ada program akan segera dijalankan. Nah, ini ya, waktu tunggunya ada 3 kan. Maka akan muncul program berhasil dijalankan. Silahkan isi di bawah ini. Nah, ya. Masukkan instruksi, terserah. Nah, di sini hanya bisa menginstruksi satu aja. Jika instruksinya terlalu banyak, maka akan error. Misal kita buat ini U besar aja ya. Kita klik, maka data telah diproses oleh ALU dan disimpan ke main memory. Datanya tadi kan U ya, karena kita masukkan instruksinya U. Lalu kode binernya itu menyesuaikan. Jadi di bagian atas di array U itu kode binernya seperti ini. 1010101. Dan ini ada output program berjalan dengan baik sesuai prosedur. Ya, kurang lebihnya seperti itu. Sekian dari kelompok kami. Wassalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. Halo semua, kalian pasti pernah mengetik pada PC, tetapi mungkin banyak yang belum tahu bagaimana keyboard tersebut bekerja. Nah, pada video kali ini, saya akan menjelaskan bagaimana keyboard bekerja sampai menghasilkan output. Misalnya kita mengetik huruf Y. Ketika huruf Y ditekan, keyboard akan mengirimkan perintah. Perintah akan masuk ke dalam keyboard prosesor. Keyboard prosesor bertugas untuk mencocokkan inputan dengan kode binernya. Selanjutnya, keyboard prosesor ini mengirimkan sinyal kepada RAM. Sementara itu, keyboard prosesor juga mengirimkan sinyal kepada keyboard controller melalui bus. Bus adalah penghubung antara komponen-komponen di dalam sistem komputer. Keyboard controller digunakan sebagai penghubung antara keyboard dengan komputer. Fungsi utamanya adalah untuk menginformasikan kepada komputer ketika tombol ditekan atau dilepaskan. Setelah dari keyboard controller, masuk kepada interrupt controller. Interrupt controller digunakan untuk memfokuskan perintah sehingga menghentikan perintah yang lain. Setelah dari interrupt controller, sinyal masuk ke prosesor. Pada CPU terdapat 3 bagian utama, yaitu control unit, arithmetic logic unit atau ALU, dan register. Pertama-tama, perintah akan dikirimkan ke control unit. Control unit adalah bagian yang bertugas untuk mengontrol segala apapun pada prosesor. Bila instruksi merupakan perhitungan logika atau aritmatika, maka ia dibawa ke ALU untuk diproses. Hasilnya akan ditampung di akumulator. Setelah itu, perintah akan dikirimkan menuju register untuk disimpan sementara. Yang selanjutnya akan dikembalikan menuju ALU. Kembali lagi ke control unit, dan control unit akan mengembalikannya keluar menuju change. Setelah dari prosesor, proses dilanjutkan ke change lalu ke chip ROM BIOS. Chip ROM BIOS berfungsi sebagai media penyimpanan firmware, sehingga BIOS dapat dieksekusi langsung secara cepat. Pada bagian bahasa biner inputan telah berubah menjadi huruf Y, atau sesuai output yang diinginkan. Setelah itu, perintah akan kembali ke keyboard controller untuk memastikan inputan, lalu kembali ke chip ROM BIOS, kemudian masuk ke RAM. RAM adalah tempat penyimpanan sementara. Setelah itu, perintah akan diarahkan bersama-sama ke monitor untuk menampilkan hasil atau output dari inputan yang sudah dimasukkan.
The first component is the control unit, which is kind of like a captain in the Army. It receives its orders from RAM in the form of an instruction, and then breaks that instruction down into specific commands for the other components. One of the most important components under the command of the control unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU, and we're ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With the compare instruction, we're not interested in the number that is output by the ALU. We only want to know how the two inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B. If the inputs are the same, then the equal flag turns on, and if both of these flags are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare instruction is over, we still need to use the flags for the next instruction, so we'll save them to a register that only has 4 inputs and 4 outputs, 1 for each flag. Once the flags are set into the flags register, the CPU is finished with the compare instruction, and it can then request the next instruction from RAM. Generally, the next instruction after a compare instruction is a jump if instruction. This combination of a compare and a jump if instruction, by the way, is very common in computer programming. Anytime there is more than one possible path through a program, the computer is using these instructions to tell it which way to go. So now that we're finished with the compare instruction and our flags are saved in the flags register, we need to tell RAM that we're ready for the next piece of data, in this case the next instruction. So inside the CPU, another register that is very important is what's called the instruction address register. The CPU uses this register to know where the next instruction should come from in RAM. When the CPU is ready for the next instruction, it enables the instruction address register onto the bus. Eventually, the instruction address will flow to RAM, but it doesn't get there directly. There is an intermediary register called the memory address register, whose only job is to tell RAM what memory address the CPU wants next, since it won't always be an instruction. Once the instruction address is set into the memory address register, it is automatically sent to RAM since the memory address register doesn't have an enable wire. The control unit then turns on the enable RAM wire, and RAM automatically sends back the data at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from RAM, which happens to be an address, and move it into the instruction address register. When the jump if equal instruction is over, the CPU then processes the instruction at that new address. At that new address may be some instructions that output the text "you guessed correctly" onto the screen, because now we know that the user guessed correctly. So we'll add the final 4 wires to our CPU, which are used to control the external devices like the monitor and the keyboard. We now have a nearly complete picture of what the Scott CPU looks like. Data moves around inside the CPU using the bus and is stored in each register according to how that data is going to be used. Each instruction that we have seen can be processed by the Scott CPU in about 6 clock ticks. Modern CPUs can process multiple instructions per clock tick, meaning that the computer you're using to watch this video is likely processing tens or even hundreds of billions of instructions per second. That phenomenal speed is accomplished by using more than one of each component and making sure that all the components are active as much as possible. This makes modern CPUs much more complicated than the Scott CPU, but they are still fundamentally doing the same things as the Scott CPU. So now let's zoom back out and we can see all the wires that run back out to the pins on the chip. On the right are the set RAM and enable RAM wires. On the top are the RAM address wires. On the bottom are the data wires that run to both RAM and the external devices. And on the left are the input-output control wires. So let's zoom back out to see the rest of the chip, and we'll put the cover back on the CPU and put it back in the motherboard. Using the ports on the left, we can now plug in the cables that connect our monitor and our keyboard. Each of these ports has an address, and that port address is what the CPU uses with an in or an out instruction. That port address, by the way, is sent using the data bus, since the address bus in this computer is only used for RAM. So we'll zoom out to see how the motherboard fits inside the computer case. In the computer case is the last component we'll look at, which is the hard drive. As soon as the power to the computer is turned off, all the data in RAM is lost, so you have to have a way to store it more permanently. For that, we use a hard drive. Inside the hard drive is a spinning disk covered in tiny magnets with a small metal arm floating above it. The arm moves around to the different parts of the disk where different data can be stored and retrieved. The disk and the arm generally move very, very quickly, but nowhere near as fast as the CPU can process data. For this reason, all the data from the hard drive must first be moved to RAM before it can be processed. So we'll put the hard drive back inside the computer and zoom out. Here we can see the program we just ran and the message telling the user that he guessed correctly. So now you've seen the very basics of how a computer processes information. You'll find much more about the Scott CPU and the book at the website buthowdoitknow.com. Also, there are a few small differences between the book and the video, but those shouldn't detract from your understanding of either. You can find a list of these differences in the video description. Thanks for watching.